started doing their filing? But you have everything else. Wow, and then you 100% for submission. Okay, so today we're going to continue where we left off. I do a quick recap with you on the model that we've learned so far, the kinetic particle theory model. After that, I'm also going to go through something called Brownian motion. This is a very important experiment because it helps scientists discover or verify also this particular theory. Yeah. Okay? So I just want to backtrack. Okay, so a recap from yesterday. Yesterday, primarily, we did kind of like a revision of what you learned in primary school. You learned about solids, liquid, and gases. First thing we did was define what matter is. After defining what matter is, we went into how we can convert matter from one state to another. Okay, and these are the various processes. What is not immediate to students is that everything in this world, because it consists of matter, can go through solid, liquid, and gaseous state. The only reason we are all solid state and liquid state at this temperature is because our boiling and melting points are very, very high. Okay? For things that exist as liquid at room temperature, because their melting point is very low. So everything can go through melting and boiling at the right temperature. For us, it will be extremely high. Other than solids, liquid, and gases, and looking at the processes, we also look at some of their properties. And this was what you learned in primary school. When you look at all these states of matter, you can describe how the shape and volume, what the characteristic of it is. We know that for solids, it has a fixed shape as well as a fixed volume. For liquids, it has no fixed shape, but it could take up the shape of the container that it has. But it has a fixed volume. Gases, no fixed shape, no fixed volume. That's what's happening on a big scale. We also went through what's happening on a very, very small scale. On a small scale, we know that all matter made up of particles, be it solid, liquid, or gas. What differs between these particles? Number one is their arrangement. But this is not a perfect model. You may have seen this in primary school before, but in reality something is very, very missing. Something that you cannot draw no matter how hard you try. And that is the movement. So when we look at the kinetic particle theory, one big aspect of this theory is that all particles are moving, whether it's solid, liquid, or gas. Except we cannot see this movement. We can best represent it using a model. Yesterday, you all used a simulation to see for yourself. So at this point in time, actually, are the particles of the table moving? They are. They're moving at vibrating a very fixed position. So overall, they don't move to a new place if you leave it over time. Liquids, however, if you were to take a glass of water and you drop one ink inside into the water, you notice that the ink droplet starts to spread. That's because all the water particles are constantly moving, helping to spread apart those ink droplets. That's why we call it the kinetic model of matter. Because at the end of the day, movement is very important, something we cannot depict, but you must be aware of. You played with this simulation yesterday, okay, about how solids, liquids, and gases can convert between one another. Okay, today we're going to spend some time looking at some of the properties that happen on a very small scale. So yesterday, one other thing that we went through was what's happening at the particle level. You should, by now in your textbook, I think that has been filled up for you, so there's nothing to copy. They show you three things that you can talk about. other than the arrangement and the movement, you can also talk about the forces of attraction. These are the 1, 2, 3 things we expect you to know when you look at the kinetic particle theory. And if you look at these descriptions, they are quite intuitive. Not too far-fetched, quite understandable. When you look at solids, the reason why the particles are so close to each other, because the force of attraction between them is strong. Suddenly want to sneeze. Don't sneeze, it's not in the mind. Number 2, the particles also, if you look at the arrangement, it's very, very far apart. Sorry, very close to each other because it's a solid state. Other than that, they do move, but they vibrate about a fixed position. Kind of like you, stuck in your seats, vibrating, or very bored, shaking around, but you're still at your seat. Actually, you are very much arranged in a solid state position. Yeah, look at each other. Arranged neatly in rows, columns, are moving, but fixed at that position. This is a very solid state. Come recess time, when I say, oh, you can go for recess, you are immediately from solid to gaseous state. Immediately start spreading and running very far apart. Maybe PE lesson is like liquid state. You are still one class, but kind of running in there, someone bumping into each other. Okay, so liquid state, you still expect the force of attraction to be very high. Like one class, you still be together. You are still quite closely packed, but not very orderly. Like during your PE lesson, you're playing a game. You, when you look at the movement, you'll be moving about, sliding over each other. Okay, that's not what you do during PE. Be very odd. But for gaseous state, the force of attraction is negligible. All the particles very far apart. You look at the arrangement, also you find it to be very far apart. Movements, they kind of bounce off each other, quite random. They're moving at very, very high speeds. Okay, so we expect you to know these descriptions at a very high level. So I do expect you to remember these 1, 2, 3, 9 boxes. You may want to star this box because this is a very important part of the chapter. A lot of things that you'll use to describe what you observe for solid, liquids, and gases, you can just plug from these 9 boxes and put it into your answers. I'll show you an example in a while. But before that, we're going to look at the history of the kinetic particle theory. How did scientists realize that although substances don't look like they're moving, they actually are? We're going to look at the story of this famous scientist, biologist called Robert Brown. Interestingly, he's a biologist that discovered the foundations of this kinetic particle theory. You should have a E and I 8.2 with you now. If I get you to take out E and I 8.2. When you look at E and I 8.2, I would like you to see a particular observation that Robert Brown made as a scientist. It was the most hyped thing of his time. Our time is the handphone, but back then, one of the most sophisticated piece of equipment and gadget you can get, and very expensive, was a microscope. When the microscope first came out, it was the hot item. Scientists or not, everybody wanted to get one because they heard that it was very amazing. You can see things that you cannot normally see. Robert Brown, biologist, of course, this was something he needed to get. A lot of scientists, like Robert Brown, after they got a microscope, they discovered so many new things. He discovered a lot of small little biological structures we didn't know existed. This was one of the first things Robert Brown saw under the microscope. He wanted to observe, as any biologist, very curious. He saw flowers, and on the flowers, he noticed a lot of yellow, small little particles that are falling off. You know what those are? Starts with a P. A pollen grain. So he's very curious. He's very curious about what pollen grains look like under the microscope. So this was what he did. He took a little droplet of water, he put it onto a glass slide, then he dripped that drop of water onto the cover slide, after which he put the pollen grains into this droplet of water. And then he put it under the microscope, and this is what he saw. Okay? This was was what Robert Brown saw. And he was very confused. Okay? He didn't expect this to happen. He took a second look. He realized what he saw was indeed happening. He noticed that the polar grains were moving. Okay? So first thing I'd like you all to discuss, you see that column above. They say, what do you observe in the video? I'd like you to write down as much observations as you can see. We're going to talk about it in a while. Then let's try and make sense of that observation. What do you see in this video happening? These are the pollen grains in the microscope. Okay, write down in words. What do you observe happening? In your own words. You are Robert Brown. What would be the first observation you write down in your logbook of your research? Okay, teacher says it looks nice. There are many observations you can make when you see this. Okay, Joe, what observation can you make? They seem to be vibrating in their position. Okay. Kamyo, what do you see? Same thing, you also use the word vibrate. Chunha, what do you observe? Okay, they don't seem to be moving very far. They are moving, but you don't see them like scattering around, okay? Evie, what do you observe? Sorry? Okay, you seem to be vibrating on the spot. Megan, what about yourself? Okay, they seem to be very close to each other. Any other observations? Okay, they are not moving very drastic regions. They seem to be kind of close vicinity. They're kind of moving around the region, right? Not very far apart. Why do you think this is happening? In that box below in your worksheet, these are some of the viewpoints that many people have. I'd like you to look at all the points brought up inside that box below. We have 4 different individuals. Each one of them have their own idea of why the pollen grains may be moving. These are the same thoughts that came into Robert Brown's mind, as well as many scientists around him. I'd like you to give a read those 4 different conclusions that were made by scientists of that time. Maybe you see dust particles there, so that's an error. It should have been pollen grains. Actually, so it should have been pollen grains. So there are 4 different observations. Rob says the dust particles, perhaps they are being blown by the wind. Dust particles are gases, or the pollen grains are gases. Maybe that's why they're moving. So the pollen grains, because they are solid, and they are also moving freely. They say that the pollen grains, maybe they are made of many particles. And is it too big? It should not be moving. So a lot of different observations being made here. What do you think? What do you think? So you are now Jane. Hey boy or girl, you're all Jane now. I'd like to hear your views. Why do you think the pollen grains are moving? Will you flip to page 2? So there were 4 different people, from Rob all the way to May, Adam, and Ellie. I think that's how you pronounce the name. Out of all these 4 individuals, which individual do you feel like you want to agree most with? Or do you find that you want to disagree with all of them? So I give you a few options. If you disagree with all of them, could I get you to write down in anywhere of the space what you think is happening and why the pollen grains are moving? But if you find that you agree with any one of them, could I get you to elaborate a little bit about why you agree with them? Okay, I'll give you around 3 minutes to do so. Now let's listen to your point of view. We role play, we go back to Robert Brown's era. Try to figure out what is on everyone's mind. I say again, if you disagree with all of them, I would like you to, in that blank space, to write down what you think is causing the pollen grains to move. But if any one of them you agree with, I'd like you to just write beside your name why you agree with them. Okay, let's listen to some of your views. So I hear your thoughts. What you think about what they saw. So as I walk around, I saw some of you describing dust particles, some pollen grains. So the interesting thing is, when Robert Brown looked at the pollen grains in water, he saw this happening. He did repeat this same experiment, except this time he had a box. Inside the box, he had a cutout so that he can see what's happening inside. Inside he burned a little bit of paper so that he allows smoke particles to float inside this box that is filled with air. He also looked inside the just like how we looked at the pollen grains in water. Actually, we saw kind of the same thing. Okay, so let's look at who you agree with and who you disagree with. Just want to hear some of your views. Shivani, I saw you return something in the first sentence. Okay, what are some of your thoughts? Right. Okay, so Shivani says actually she thinks she agrees with Rob because when you look at wind, it's kind of caused by the environment, cannot control. So could that have caused these small little microscopic vibrations and movements? Okay, so that is Shivani's point of view along with Rob. Thank you. I like that you contributed where the wind came from. Yeah, it came from the environment, not from the pollen grains or the dust particles themselves. Okay, what about Megan? Oh, I asked you already, right? Okay, behind. Anshika, what about yourself? You agree or disagree with anyone strongly? Agree with me. Okay, what did May say? May says that dust particles are solid and they are moving freely. Okay. Okay, yeah. 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 Right, okay. So are you thinking along the lines of, when we look at the dust particles, they are, because we said that solid state, they are made out of particles, right? So are you saying that because they are kind of vibrating on the spot, that's why we observe this? Okay? So that's what Ashika says. So, but remember this, right? When we say solid state, when we look at solid state, actually the particles are moving individually about a fixed position. Okay, any more points of view? Shuya? I haven't heard from you in a while. I can call you. What do you think, Shuya? Agree or disagree with anyone?
Can I do someone that's already
Sure, yeah. It's fine.
I disagree with May.
Okay, Shuya disagrees with me. Why?
I feel like the particles aren't moving freely, they're just like kind of vibrating on the spot.
Right, okay. Okay, Shuya is saying that, Shuya, are you saying that, are you replacing particles? Are you referring to the darts? Because each dust is made out of many individual particles joined together. Are you referring to the particles of the dust solid?
The particles of the dust.
Okay, so when we look at each dust solid, so each dust solid looks something like that. But we were to zoom in, we will find that it's made out of many of these particles. Okay, so Shuya is saying that each particle is kind of vibrating on the spot. But which part do you disagree?
Like it's not really like moving
Or are you saying that these particles aren't really moving like liquid state? They're not moving here and there.
yeah.
So therefore, you disagree with her saying that because these particles are moving, therefore it results in this entire large solid moving. Are you saying that? Okay. So we have a little bit of differing views here. If we go back to Hanshika as well as Shuya, so Hanshika feels that when because we learned that in solid state, these particles are moving and vibrating on the spot. Could that result in each of these solid dust to be vibrating on the spot as well? Shuya, on the contrary, believes that when they vibrate on the spot, you shouldn't observe them moving as a result. When we bring in Shivani's point, Shivani says that therefore she perhaps feels that it doesn't come from internally, each of these solids. Perhaps it's coming from externally. Maybe it's the external environment that's causing it to move. Okay, so what I like about what you just done here is really what the scientists back then did. They didn't have the answers, but they went back and forth. Many different theories as to how this might be happening. One other question that came to mind, thank you to all of you, that wasn't written here was, okay, we look at dust, dust is not alive. But when we look at pollen grains, they are alive. So could it be that because the pollen grains are alive, that's why they're moving? Emily, you're shaking your head. Yeah, what do you think?
Actually, the scientists also conducted the experiment on already dead palm trees.
Fair enough.
Also, the reason why they're moving is due to the collision with the fast-moving atoms from the place that it is suspended in.
Okay. So Emily kind of just went a few steps ahead. So what Emily has just done is after many years of debating before they came to the conclusion. So remember I told you this was Robert's first experiment. He wondered, could they be moving because of the wind? Could they be moving because the polar grains themselves are alive and moving? Could they be moving because these individual particles that make up the polar grain are themselves vibrating? So actually, the dust particle one was one of the next experiments he did. Because the polar grains are alive, how about I do it with something that's not alive? This was what he observed. He tried the same experiment with fat droplets as well as with dust particles. And he observed exactly the same thing. Okay? These non-living things are also moving. Okay, so he's ruled out one thing. Definitely they're not moving because they're alive. Could they be moving because of what Ashika said? Could the wind be a factor? So, how could it move? Actually, it goes back to the kinetic particle theory. Yeah, so I'd like everyone to try this particular model, this simulation. Let me go to this simulation. Yeah, you have your iPads with you. You can scan this simulation and it should bring you to a particular page that lets you see the particles. So not particles. It lets you see the pollen grains or the dust or the fat droplets. Hopefully it gives you an insight as to why they are moving in the way they are moving. If you scan the QR code, it should have brought you to this particular simulation. This one. Have this. Here, I have a few pollen grains. They are kind of moving a little bit. Are you on this page? Just give me a nod if you are. Oh, you haven't scanned it. Okay, just give me a nod if you are on this particular page, yeah? Okay, so I have quite a number of you there. Karen, got it? Okay. For those of you that are very fast, you can start toggling other things. How about you toggle this part? Drag to see what's actually going on. Remember, the pollen grains have been put into water, so I'm going to drag to reveal what's happening. When you drag it to the right, you will be able to see the water molecules that the pollen grains have been suspended in. What do you observe? But when I take away this particular point of view, all I see are the pollen grains, kind of moving in this very jittery fashion. Which is what we see under the microscope. What we don't see is this. You can play around with the other features. What if I increase the energy? What if I make the water hotter? To increase the energy, what am I referring to? I'm increasing the temperature of this water. Wow. Okay, if you increase the temperature, what do you observe about the particle? What do you observe about the pollen grain? Well, they seem to be moving a lot faster. Moving a little bit more. What if I change the Okay, we don't play with the other two features because they are not really showing you what it's supposed to show. Okay, so this is what we saw, the pollen grains. They look like they are behaving in this way. If you were to click trace path, it will even show you how they move. If you were to track to the right, it will show you what's happening in reality. So what can we conclude from this experiment? I'm bringing us back here. Okay, in your textbook, this is the page I'm at currently. You should be going to page 22. Page 22 of your textbook is where I'm at. Okay, madness on some of your screens. Some of you have pushed the simulation to the max up. Yesterday, the simulation of solid, liquid, and gas. I remember who increased the temperature until the simulation exploded. All the particles inside, this person increased the temperature until the particles flew out of the whole simulation. Didn't even know they can do that. All you are. Okay, how you broke the system. Okay, may I get you to put your iPads aside? Unless you are using it to take notes. So, could I get you to pen down in words? This was what we observed. If you look at your textbook, it shows you the diagram. It shows you the movement of the polar grains. I'd like you to write down in words how to describe this movement. Many of you say vibrate. But vibrate is slightly different from moving jerky and randomly. Yeah, okay, that's what causes it. Okay, so rather than write vibrate, because to vibrate kind of means you're kind of on the spot, not moving anywhere. Instead, you write this down in the box on the left hand side. In words, the fat droplets are moving jerkily, and randomly. Okay, try not to use the word vibrate. Then, they give you a small long rectangle below. How does the kinetic model explain the behavior? Okay, actually, the fat droplets and the pollen grains are moving that way because the water that is suspended in, the water molecules are colliding into it from all different angles. That's why they are moving in that way. But because they collide into the particles at such random places, it's very uneven. That's why they move in a rather random fashion. So as a class, we have experienced or observed the phenomena resulting from two different experiments. Yesterday, we mixed ethanol and water water, and for some reason we were missing volume at the end of the day. What was the explanation for that? Well, because there are actually spaces between particles. That's the first part of the kinetic particle theory. When we look at particles, especially liquid and gases, you often find that there are spaces. Gives us an idea of what's happening microscopically. Microscopically. When we look at the Brownian motion, this particular experiment, we find that, okay, how come we can observe these pollen grains or the dust or the fat droplets moving in a jerky fashion? The explanation for it is because it can be explained by the liquid or gas particles colliding into it. What does this prove? It actually proves to you that when you look at liquids and gases, the particles are moving even though we cannot see it. If you just take a cup of water or you just look at the air around you, what evidence do you have that indeed they are moving particles? You cannot see, right? But this experiment is very strong because it proves to you that actually the air around us and the water in your cup, they are actually moving even though we cannot see it. The best proof for it is to drop a little bit of dust or pollen grain or maybe fat droplets and you will see them move. Why are the fat droplets moving? Because the liquid particles themselves are moving. And I think that's why the simulation is very beautiful. Because it helps to make visual what cannot be seen. So let's go to the question below, some thinking questions. I said so many times that this is happening because the water molecules are moving. But A, why are water molecules not observed in real life? What do you think? Okay, thank you, Kara. Why are the water molecules not observed in real life? Because in reality, it's too small. We cannot see it. Even with the microscope like Robert Gao, we will not be able to see the water molecules. So the best evidence we have that they are moving is by the movement of the fat droplets or the pollen grains. They are too small. You just cannot see them moving. So we need to find other creative ways to explain why it's moving. Yes?
Using an electron microscope.
Oh, okay. Good question. Could I see water molecules using an electron microscope? To my knowledge, electron microscopes cannot see atoms yet. Okay? There are, I know, even more powerful microscopes that could allow you to see down to the atom level. But actually, an electron microscope doesn't go to that level yet. Atoms are actually really small. What do you think will happen if I have fat droplets that are heavier? How do you think you'll influence its movement? Okay, Ethan says perhaps you'll move slower. Actually, it kind of is. Imagine you have one small ball, and then all of you are kicking the ball during PE lesson. But if a teacher suddenly brings a heavier ball, you're trying to kick, likely that ball is going to move much less. So, whatever the object is that you're putting into the water, the liquid or the gas can influence how it moves also. Because how heavy it is, how much mass it has. If the fat droplets are heavier, you can expect that they will move slower. Their movement won't look like this anymore. So random and changing all the time. You'll find that with a heavier particle, it kind of moves in less directions because it takes a lot more energy for all the liquid particles to hit it, to move in a collective direction. Okay, so the words we can describe are, it will take more collisions for a specific direction to occur. Therefore, it won't be moving in this crazy, erratic, jerky fashion as much. The heavier a particle is. The particle is extremely heavy. Like if you put a pebble into a glass of water, you won't even see it move at all. So actually, if the solid you're putting into liquid or gas is extremely heavy, you won't see the entire thing move. But if you were to go down to the particle level, they are still vibrating on the spot. I want to come come back to Hanshika's point and Shuya's point in a while. Sorry? Okay, I want to come back to Shuya's and Hanshika's debate earlier on. We haven't answered one question. Could the dust, the pollen grain, the fat droplets, could they be moving simply because if you were to zoom in and look at each particle, they are vibrating on the spot? Could these individual vibrations on the fixed positions be causing the entire dust particle, the entire dust or pollen to be moving too? Ethan says he thinks that the vibrations are too small. You shouldn't be able to cause this entire pollen grain or dust to move. Okay, what do you think therefore? What experiment might I do next to prove that the movement of the dust or the pollen grain is not caused by the colliding liquid particles or the colliding gas particles? I'd like everyone to think. What experiment could I do to prove that? I say again, what experiment could I conduct to prove that the movement of the dust and the pollen is not due to these individual vibrations of its own particles, but because of the liquid and the gas particles bumping into it? What experiment could I do? Ethan says put on a flat surface and see if it moves. Kyle? Same. Put on a flat surface. So meaning don't even put it in.
Put it under a microscope.
Okay, put it under a microscope, but don't put water.
Yes.
Right? Okay. But remember, the dust experiment was put in a box of air. So isn't that very similar to what you said? Just put under a microscope. Yes, yes. Yes says, why don't we put it in vacuum? What is a vacuum? A vacuum is somewhere with nothing. Yeah? Vacuum is devoid of air, no liquid. If we put the pollen and the dust inside vacuum and we observe that it doesn't move, would that prove that any movement was caused by the liquid and the gas? Yeah, actually that was quite a smart way to prove up. And the experiment was done. In reality, when you put it in a vacuum, the dust and pollen does not move. Even though its individual particles are vibrating on the spot. What does this show? It shows what Ethan was trying to say earlier on, that these vibrations are not strong enough to cause the entire thing to move. Okay? In fact, because they vibrate all collectively on the spot, you observe nothing happening on the big scale. That's why your table doesn't move. You leave a marble on the table, it's not also going to roll up by itself. Unless there's some spirit, some ghostly energy around it that helps give it a push. Okay? Okay, so this experiment is a very special experiment. I want everyone to remember this. We describe that jerky movement. Okay, we describe this jerky motion as the Brownian motion because it's named after Robert Brown. Okay? And then he had to name it after himself. But this time, if you all discover a motion, just name it after yourself. The Hanshika motion or the Shuya motion. Okay? So he named it after himself, the Brownian motion. This motion explains a lot of things. It explains that liquid and gas particles actually they are always moving. Okay, last part of today's lesson, we're going to do a checkpoint. If you look at checkpoint 1 on page 23, they gave and gases. For example, let's look at solids. For solids, it says that solids have a fixed shape. So earlier on, remember I said that for this particular chapter, I need you to know page 21 very well. All those 9 descriptions in there, you need to know very, very, very well. To save you some time, this is what I'd like you to do. Can you go to page 9? I'd like you to number off page 9. All of those 9 boxes. So what do I need? Okay, you have 9 boxes. Can you go in this particular sequence? So it looks like that, right? Then after that, it is solid, liquid, gas. Okay, could you on the top right hand corner put A, B, C? Okay. Add in a little bit more. Sorry, so this one A1. So now A2, A3, B1, B2, B3, C1, C2, C3. Why am I asking you to do this? Because when you look at this particular page over here on page 23, I'll give you an example right now. Normally what teacher will ask you to do is to copy a lot of words. But I want to show you that it's not about copying, it's about knowing which of these description best matches these empty spaces here. So I'm going to show you an example right now. Now I'm going to give this to you as a little homework. Okay, let's look at solids. Solids are known to have a fixed shape. But which one of these descriptions, A1 to 3, B1 to 3, C1 to 3, best explains why solids have a fixed shape? So everyone go back to page 21. Look at all the descriptions there. Which description here best explains why solids have a fixed shape? Okay, and you just tell me the alphabet and number. Which description best describes why solids have a fixed shape? Olivia? Sorry? Okay, Olivia chooses A1. Let's look at A1. It says, well, solids have a fixed shape. Could it be because they have very strong forces of attraction between them? Yeah? Could it be? You try to show something. Sorry? Oh, then what did you choose? You chose A? C1. Oh, you put C1, okay. So for solids, she chose C1 as the best description. That the particles vibrate about their fixed position. Could that explain why it has a fixed shape? Okay? So I show you a sample of the answer. So solids, they are solid and they have a fixed shape, meaning they don't change shape. Because number one, the force of attraction needs to be very high. Number two, they also have a fixed shape because they are very closely back to each other. Okay? So here's an example. Can you see that for solids, it's a mixture of writing down A1 as well as A2. Solids have a fixed shape because of A1. They have very strong force of attraction. And A2, they are held in fixed positions, very close to each other. Actually, it's more A1 and C1, right? Like Olivia said. Okay? I take it back. Particles are in fixed positions. So you look at C1, but particles vibrate about their fixed positions. Okay, and they are held together by very strong forces of attraction. Okay, next, liquids. Why do they have no fixed shape? Because of A2. They have strong attraction, and as well as C2, because their particles slide past each other randomly. So do not write the whole paragraph like what you see on the screen. Save time. Will you just identify out of A1 to 3, B1 to 3, C1 to 3, which combination of this can best describe the phenomena that you observe? Okay, so that is the homework. So thank you, Olivia. So Olivia is a mixture of A1 and C2. A1 and C1. Yeah? So you try this out for the rest of the descriptions. And tomorrow, for our last lesson, we will just run through what descriptions you think best explains explains all these properties here. Okay? Don't need to write it out. But for yourself, eventually you need to remember all of this. Because, for example, I may ask you a question. Will you explain to me why solids have a fixed shape? Then you must be able to choose the correct combination of descriptions to write down. Okay? So that is your homework for today. You have 2 more minutes. You could try now to choose the correct combinations of descriptions to explain all of these phenomena. Why does solid have fixed volume? Why does solid have high density? Which description best describes? Nice little casing. I don't know what species of moth this is. I will need to find out. But thank you so much. I need to pass the container. Whose side is this? Yours. It's in your house for 2 days, then it died. So you saw it in your house for 2 days flying around. Oh. Then how you know it wasn't dead for 2 days already? Oh, then the 3rd day it was on the floor. Nice. Okay, thank you so much. I will spread his wings and pose it properly. Then I'll try to find out what this is. I'll take a nice photo, then we can find out what this insect is as well. Thank you so much. I've not seen this in my collection before, so I have no idea what it is. But you have contributed to the pool of insects that your juniors will next year see. Yeah? Okay, but to admit, because I teach every alternate year, that means next year's JH1 will never see the insects. You have to wait for another generation. Yeah. It's just nice I got to teach your batch. And I like insects. Okay. Sorry, I think I already passed the timing. What is it now? Well done. Okay, just nice it's 12:30. Thank you so much for today's lesson. Okay, so tomorrow we'll run through the